Friends, my name is Pawan Kumar Upadhyay. I am back again with another small recap on MRI machines and its hardware and about MR Basics. Actually, when we try to collect all the MRI basics and other theoretical details, it takes longer time. It takes long time to prepare ourselves and make the videos. So I try to work hard and collect videos and collect materials for you. I study, I prepare myself, and then I present the videos. That's why I take little longer time. So I'll try to make much faster videos and quicker in future. Okay, if you like my videos, please share these videos to your friends and subscribe my channel. So let us see about these MRI things. As you can see here that this is the basic overview I have tried to summarize here. It's an MR overview. This is the magnet. The patient is lying here in this magnet, and this axis you can see it's a Z axis, Z axis. Okay, plus and minus in this direction, plus and minus. Okay, plus this side or maybe minus this side, or plus this side minus this side. Okay, so B0 is a magnetic field due to the magnetic field vector. This patient is lying in Z direction. So in the bullet points you can see the patient is placed in the magnet, RF is applied, then RF is off, and then patient is releasing a signal, RF signal. When you give RF to the patient, okay, and when you remove this RF, the patient emits the RF. That this RF emission is weak RF. This is also RF. So this RF we have to capture in our receive coils. This is the MR signal. Okay, so RF is applied, RF off, patient emits signal, and this signal is processed by the imager. Some companies call it recon tower, MCIR, MRIR, MARS, MARS, etc. So this is a high class processor, and it is doing the recon activities with a Fourier transform. We will see detail in the next slides. As you can see in this slide, why I chose this photograph, hydrogen atom. In some books you might have studied that protons are there, hydrogen atoms are there, all are same. When the writers describe MR physics, they use hydrogen atom, protons, all are same, because this electron is out and this atom is nomenclatured as proton, H plus, because the electron is out, so H plus. Proton is same, hydrogen atom is same. So why we use the hydrogen atom? Because its sensitivity towards resonance is very high, and it's the lightest weight, and it is in abundance in a human body. This hydrogen, water is, the availability of water is in abundance. So we are using this hydrogen atom for MR studies. Now what is the meaning of spin? As you can see here, that's why I have chosen very fewer texts to explain you about this. So spin, you can see here, this is the atom, is a hydrogen atom spinning its in own axis. Okay, precession, this is precession. See, precession is like this is your axis, and you are doing a wobbling like this, wobbling like a top. So this activity is called precession, and this activity is called spin. In this slide you can see that these are some hydrogen atoms. All are these hydrogen atoms, protons, H plus. Okay, they are all randomly, these are all tiny magnets. What is the meaning of this vector? This vector means this hydrogen atom, proton, charged particle, they are moving charged particles are like, they behave like a tiny magnet. So it's a magnetic moment, they create a magnetic moment. Okay, so hydrogen, proton. So all these are randomly aligned when there is no magnetic field. And if there is a magnetic field, B0 is present. See, this is a magnetic field. Okay, if there is a magnetic field, these are all aligned either in this direction or in this direction, parallel or anti-parallel. Okay, what is precession? As I explained you in previous slides, precession means if there is a magnetic field. See, this is a magnetic field B0, and this B0 I explained you is because of magnet. When this magnetic field is present, one atom moves like this, like a top. As you can see, very popular animation. So using this animation you can understand. And this is your magnetic field, and along this magnetic field, see the motion. So this is your magnetic field, and this is your vector hydrogen atom, and they are doing like this, wobbling. So this motion is called precession. So let us see the next slide. Our next slide will be So now this precision is clear to you. Now we are moving to the another slide. This is the Larmor frequency of hydrogen atom. See what is this Larmor frequency, and this is a very generalized equation of related to MRI. This is a, see, omega is equal to constant times B. See this magnetic field, this frequency, the Larmor frequency is proportional to the magnetic field, means omega is proportional to the magnetic field. So more magnetic field, higher the magnetic field and higher the frequency. So this see, this atom is doing this, what movement it is doing. This is the precession. If the magnetic field will be high, if suppose this magnetic field is more, so this precession will be very high. Okay, if the magnetic field is less, so this precession will be very slow, like this. So more magnetic field, higher the magnetic field, higher this is precession, this movement. Okay, so omega is equal to constant times B. Stronger the magnetic field, stronger the precession frequency. So now you understood about the Larmor frequency. This is your Larmor frequency is equal to the magnetic field strength. So Larmor frequency, so when you apply this RF, see this is the RF and this is the patient inside the MRI. So when you apply this RF wave, the RF wave frequency should be the same of the hydrogen atom precision frequency. Understood? So when you apply RF, this RF frequency should be the same as hydrogen precision frequency. If this is same, then what will happen? Resonance will happen, and the maximum power transfer will take place. So power can be transferred, this RF power can be transferred to the patient. Okay, and the maximum energy will be transferred. These are some small relations. 1 Tesla, what is the precession frequency for hydrogen? 1.5, what is the precession frequency? 3 Tesla, what is the frequency? So now this is a magnetic moment. As I explained you earlier, this is a hydrogen atom, and this is a any hydrogen atom behaves like a tiny magnet, and all these hydrogen atoms are doing a precession like this. Okay, so this is the movement. This hydrogen atom is precessing like this. So okay, all these hydrogen atom, one hydrogen atom is here, one is here, one is in this side, one is in this side. So all move together, and so collectively we can say that there is a net moment, magnetic moment. So for the simplicity, we can say that a net magnetic moment is aligned with the external magnetic field. So this is your magnetic field. In the same direction, there is a moment, magnetic moment. So this diagram is showing that a charged particle is moving, and then it's creating a magnetic moment. So another diagram is, another image is a little bit about RF pulse. As I explained in my previous slides about RF, two sinusoidal waves propagating each other, electrical wave and magnetic wave propagating together with a shift of 90 degree. Here in MRI we are using two nodes, 0 degree and 90 degree split. We are transmitting through two different channels, okay, to the transmitting coils. Next slides you will see. This is your body coil. Some companies say body coil, some companies say transmit antenna. This is the transmit antenna. This is the body coil. This transmits the RF signal to the patient. So, and this is your channel, RF energy, with a 0 degree transmission channel and 90 degree transmission channel. Okay, and then these two are being transferred through the VTC, through the body coil to the patient. Understood? So it's clear. RF pulse applied at the Larmor frequency, as I explained you earlier. Whatever RF we are applying, it should be the same frequency of the hydrogen precession. Means that the dancing frequency of hydrogen, the speed with which it is dancing, it is precessing, the frequency of this should be the same of this applied RF. Then the resonance will take place, and the energy transfer will happen. So this RF would be capable of transferring more energy to the patient body. So now the next slide is RF applied to the hydrogen atom. As I explained, when the RF is applied, see, this is the patient. Okay, this is the patient body, and there is one hydrogen atom here. This is the hydrogen atom. Okay, So, and this is the vector. I told you that all the hydrogen atoms are denoted as a vector. So when this RF we applied, this is the RF, and this RF is applied to a hydrogen vector. This is the hydrogen H plus, small tiny magnet. It is, earlier it was only spinning, and when we applied the RF, it is in magnetic field actually. It is in magnetic field influence. So when RF is applied, it starts precession, starts moving like this, and it gains more energy and it starts moving in a bigger diameter. See in this image, when we apply RF, it moves from here, it goes to here, and it starts moving in this plane. Hope this diagram is clear to you. This animation is very simplified one. So now we move to the another slide. This is again the same repetition. RF is applied to the hydrogen proton, and these are all magnets. See, this is the magnet and this is the vector. This is a hydrogen atom. When we apply this RF, what is happening? This RF is applied and this hydrogen atom gets flipped. Earlier, this is the main magnetic field. Hydrogen vector was also in this magnetic field. When we apply RF, this hydrogen atom takes a theta angle. This is the magnetic field B. When we apply RF, it takes a theta angle and moves like this, and precision starts bigger in the bigger diameter. So now let's move to the another slide. RF is applied to the atom. Again the same slide. Now we can apply two types of RFs, 90 degree RF, 180 degree RF. Means this is a main magnetic field B0 and your hydrogen atom is here, okay, H plus. When you apply some RF from here, when you apply RF, so you can apply 90 degree RF. So after precision, this hydrogen can go in 90 degree plane, okay. When you apply 180 degree RF, this hydrogen atom can go here, this side, 180 degree. So I have tried to explain in this slide. You can see here 90 degree RF, hydrogen is here, from here it reached here, and 180 degree RF, from here it reached here, 180 degree RF. Now another slide is MR signal. After RF removed, you remember I explained in the first slide, you have to apply RF and then you have to remove the RF. You can see here, now your RF is removed, now no RF, and see, so whatever, this is your this is the vector, it's going in home position. Now earlier this vector was here 90 degree or 180 degree, now it's trying to go to the home position, and the path it is following, see, it is a spiral path, helix path, very complex. So we try to break this into two vectors. This is your hydrogen atom. Earlier it was here, some in this plane. Now it's trying to go to the home position, and it is taking this spiral path. So to understand what we are doing, we are breaking this hydrogen atom into two vectors, in this axis and in this axis. So this one we call it like, suppose, H sin theta, and this one we call it as, suppose, H cos theta, okay. So the time it is going like this. So the projection is this vector, and this here the projection is this vector. So this vector, the time this vector is taking to come to 0 and the time this vector is taking to come to 0 is called T2 time and T1 time. So T2 is called transverse relaxation time and T1 is called longitudinal relaxation time. I have another detailed videos on this. I am not going in much more details, so hope you understood this, okay. So two relaxation times are there. The relaxation times means from the excited state, the atom is going to the home state, and the returning back time, we have two different style of going back. The hydrogen atom has a two different ways. The way with which it goes back has two different styles. So that style is called T1 and T2 timing. The timing that this hydrogen atom is taking, for the simplicity, we study this as a T2 relaxation time and T1 relaxation time. I will explain because it will take long time to explain. So hope this previous slide is clear. T2 relaxation and T1 relaxation. Now this is the T1 relaxation time, T2 relaxation time, proton density. So these are all a different lecture is mandatory to explain all these things. So those are the things I am not including here. So you just see T1, this is a T1 image, this is your T2 image, This is your proton density. So images are different for T1 image, T2 image. Some in this image CSF is gray, another image CSF is black. So these are all clinical things. So now let us move to some basic about MRI components. The main components are magnet, gradient. So magnet, I think it's not drawn here. So this is your magnet. Okay, you can draw a magnet. Copper windings, all niobium, titanium, some special material. Okay, this is your niobium titanium material, copper mixed, very high class superconducting material, and there is a winding here, and this is a B0 field. When you give the current in this coil, a field will get generated. So this is a magnet, gradient coil, and RF. These are the two important components. So as you said, as you saw this slide, now we'll go to the next one. Magnetic resonance imaging. This is the whole MRI machine I have tried to summarize here. Okay, means this is the magnet, gradient coil, RF coil, all these things. So this is your MRI bore. Okay, inside the MRI bore, the patient is going. This is your B0 magnetic field, and this is your equipment room, cabinet room. Okay, this is very difficult to understand. We will see another slide. Now this is much simpler in comparison to the this one is very simpler. This is a magnet, this is a gradient coil, and this is a RF coil. All are in the same tunnel. Okay, this is your tunnel, looks like this. Gradient, this is a magnet, gradient coil, and body coil. All are in the same tunnel. Okay, and from the outer side you can see it as a one. Magnet, gradient coil, RF coil. For RF we have some electronics. For gradient we have some electronics to control. For magnet we have some controller card, something. So all these components, magnet, gradient coil, and RF, need some electronic controllers. So this is a cabinet. So cabinet room. Inside the cabinet room there are controllers, servers. These are all controlling your performance of RF coil, gradient coil, and magnet coil. This is the console room. It's a separate room. From here the operator runs the machine and images are getting acquired. Now this slide is I prepared to make you understand about the water flow little bit, how the water is flowing. Actually this is the chiller installed mostly outside the hospital, outside your MRI department. It's an outdoor unit. It supplies the chilled water. One side chilled water is going and water is coming, mostly 10 degrees centigrade. Okay, so this chilled water is going to different places. Okay, you can see the chilled water is going to, in some companies, these are the cabinets, maybe different names for different company. So these electronic components are using this water system. There are fans here. The water goes inside and this fan runs and gives cold air. Okay, so all these electronic components stay in a healthy condition, in cold condition, and then some other water is going to MRI room. See, this is a filter plate, MRI room, and the water goes inside the gradient coil. Okay, this is the gradient coil, water is going inside, and there are some other electronic boards, water goes inside, and then the hot water returns back to the chiller. So very important to understand the role of water supply and their importance in MRI machines, because it's a very essential thing. Again same diagram, MRI, magnet, gradient coil, RF coil. This is the magnetic bore, patient table, and this is your Z direction, P0 magnetic field. Again same diagram, 0.2 Tesla, 1 Tesla, 1.5 and 3 Tesla. Different magnets are there. So if you see the cross section, you will see the MRI machine. If you cut from here, you will see body coil inside, gradient coil are there inside, shimming coils and magnets. If you draw like this, there will be inside, there will be this is outer one is a magnet, then gradient coils are there inside, then body coils are there inside, and one more thing, shimming coil you saw here, shimming coil. So these shimming coils are inside the gradient coil, GC. Mostly inside the GC, the shimming coils are there. It is a factory design, and this is a BC, body coil, and this is a magnet. Okay. Now again, the overview of magnet. I explained in my earlier presentations about MRI overview and all. So this is a magnet with helium field. This is a winding inside, niobium titanium niobium material, and so its helium is inside, minus 269 degrees centigrade helium is inside. This is a turret, and filling port and other things are there inside. So if we go in more details about this magnet, we will lose more time. So you can see my other presentation. So I am moving now at this time, and you can see this 5 Gauss line. Okay, this is a magnet, this is a 5 Gauss line. My basic purpose was to explain you the fringe field, the field that is not inside the magnet, the flux that is not inside this magnetic field and it is going outside the area is called fringe field. So our purpose is to control the fringe field. We should not allow these stray fields like a stray dogs. Okay, so we have to control them, and to control the fringe field. And one thing, this 5 Gauss line, okay, this is the 5 Gauss line, 0.5 millitesla. So if any pacemaker guy crosses this line, it's dangerous for that person. So we need to be careful. We should not cross this 5 Gauss line. So how to control this stray field, fringe field? Passive shielding, active shieldings are there. Okay, active shieldings means the company will design some methods, some coils, and company will put inside, and company will try to reduce the field. Passive means outside. You are applying some shielding so that stray shields, fringe fields cannot go out. That is fringe field. So 2 methods are there: passive shielding method, active shielding method, to reduce the fringe field. Homogeneity. The diagram I think is self-explanatory. Homogeneity is very, very important for image quality, because the magnetic field strength, because each and every point, if the frequency, if the magnetic field is same, the frequency should be same for the homogeneity. Otherwise that magnet will not be homogeneous. So we need to do some methods for homogeneity, and that method is what? Shimming. This is the shimming plate, and these are the small metal pieces. Normally when an MRI engineer is doing installations, you see this guy is doing installation, doing a hard work in the field. He is putting these irons inside the gradient coil. So this activity is called shimming, to homogenize the magnetic field. See, to achieve this homogeneity, to achieve the same frequency, you need to be homogeneous inside the magnetic bore. Okay, so homogeneity is clear, and the process is called shimming. Passive shimming and active shimming. Active shimming means that is something related to the machine, to the company technology. Company has some software methods. They will give some currents, or they will drive some input signals, and they will do fine adjustment. But the passive shimming means core shimming we will do in the field, like metal shimming. Okay, so now the gradient coil, most important part, gradient coils. We will not see more details about gradient coils, but you can see there is something called X gradient, Y gradient, or Z gradient. See, this is X gradient, this is Y gradient, and this is Z gradient. So now you can see this X gradient, Y gradient, and Z gradient explanations I have made, and you can see this. You can understand by seeing all these explanations. It's self-explanatory. I can say that it's a X gradient means there is a variation in X direction, the field variation in X direction, field variation in Y direction, field variation in Y direction, and here field variation in Z direction. When the magnetic field is on, okay, then the gradient is also on, and when the gradient is on, all the hydrogen atoms, these hydrogen atoms starts, see the precession frequency is different here. You can see the precession frequency is different. Here it is different, here it is different. Okay, so gradient is on, and when the gradient is off, and field is always on. Okay, magnetic field is always on. So what we do, we sometimes switch on the gradient, or sometimes we switch off the gradient. So when we switch on the gradient, there is a gradient field, there is a field variation, means frequency variation, means the hydrogen dancing speed will vary. Here they are dancing in the same speed. Okay, so here the gradient is off. So we will see in another videos or maybe in another slides about gradients. Just keep in mind, with no gradient they will dance in a same precision frequency, and when the gradient is on they will dance in a diversified manner. And this is very, very important for us for spatial encoding. And here much more detail about this gradient coil. This is a X coil, you can see here, Y coil and Z coil, all are embedded together, X, Y and Z. So actually mostly what we learned, these gradients are used to vary the field. When these gradient coils are inside X coil, Y coil and Z coil together, it's called XYZ coil, together it's called gradient coil. When this gradient coil is inserted in the magnet, see this is the magnet, see the magnet, when this gradient coil is inserted, means X, Y and Z coil inserted inside the magnet, and when the gradient is switched on, what will happen? When see, this is the magnet, okay, and this is your gradient coil, and when this is the B0 field, all homogeneous, here and there all homogeneous. When this guy GC is on, it will change the magnetic field in X direction, in Y direction, in Z direction, as I explained in previous slides. X, Y, Z variations will take place, and what will happen, I explained you in previous animation, the hydrogen atom precision speed, the dancing speed will be different. If there is no gradient, the hydrogen precision will be same, there is no precision. Okay, all will precess in the same frequency. So we need that variation for spatial encoding. You will see how. Another diagram, I had another very good diagram. This is a gradient coil outside, this is magnet, these are the tools. These are all important for the field engineers. Now we are not going in much detail about spatial encoding, how X, Y and Z encodings takes place in gradient. We will see in another videos, because that is too lengthy explanation. Okay, now RF, some electronics is involved here. Okay, you see this is a magnet, okay, and we have this RF generator. We generate this RF, we give this RF to, this is a coil, self-explanatory. We give this RF, and when patient emits the RF, the signal comes like this to RF receiver, controller, and recon takes place, image, and this is the image, Fourier transform takes place. This is precision, flipping, 0 degree, 90 degree, all I have explained in previous slides. Another same repetition. This is your RF transmitting antenna, and this is your receive coil. So this is the RF coil, body coil, and this is the connector where you connect your receive coil, like head coil, like body coil or any other coil. This is your body coil, okay, 0 degree and 90 degree. This is your RF amplifier. When you amplify and some small signal units are there, different companies, different electronics give a signal, how much you have to give, and then accordingly RF amplifier generates the RF and gives to the another electronics, okay, and then this electronic splits in 0 degree and 90 degree, give to the patient body, give to the body coil, and this coil gives to patient body. This is the LP coil and CP coil. Two body coils we have seen in our experiences, a circularly polarized coil and linear polarized coil. Linear polarized coil means two set of coil assemblies, means the two windings are there, one set of windings. Okay, linear LP coils are used in a single coil system, they are cheaper quality, and two separate set of coils shifted with a 90 degree. I explained you, one set is this one and another set is this one. Okay, so these are more costlier and more better performance. So this is just like a summary. Now it's too lengthy, so I am trying to summarize. We apply RF, okay, to the hydrogen atom. See, this is a magnetic field, This is a hydrogen atom. We applied RF 90 degree or 180 degree, whatever, and this flips. Hydrogen atom flips like this. So we apply RF. This hydrogen atom flips like this. Okay, and then at the same time when we apply RF, we apply a gradient, X gradient. Suppose one gradient is applied, it's called slice selection gradient. And then what will happen in the magnet, a gradient will be applied, and then this patient body will be divided into different slices, because when we apply this gradient, slice select gradient, the patient body will feel a slice variation, a field variation, and different slices can be calculated, determined. So this is a slice selection gradient. I am not explaining this again. I am telling you, I have a better and detailed explanation, separate video. Please see that. I have put my lot of effort to explain that. And then another gradient is phase encoding gradient. You see the repetition, tuck 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 tuck. These are multiple steps. If the slice matrix is 512 by 512, the steps will be like this, same 512 phase encoding gradients will take place. And then this is the frequency encoding gradient. After that, first slice selection gradient will be applied, then Y gradient, phase encoding gradient, then frequency encoding gradient. This is the readout, this is the signal. When you apply this gradient, you take the signal. This is your MR signal, and this MR signal is like a time domain signal, okay, analog signal. This is your time domain signal, and then this time domain signal we use Fourier transform to get it into frequency domain signal. So time domain signal is converted into frequency domain signal. Okay, same slide. Time domain signal we use Fourier transform, analog signal converts into this spikes, this frequency domain signal, and this will be a K space. The filling will, the method is called K space, time domain to frequency domain, and it fills a K space, and signal will look like this, the image will look like this. K space image is like this. Remember, that's why I'm repeating it. Time domain signal converts into frequency domain signal with Fourier transform, and that method is called K space, and image looks like this, K space image. This is not the actual image, this is the K space filling. Again, the time domain signal, see, if there is a matrix 512 512, so this is the phase encoding steps, tuck 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 tuck, one phase encoding, another phase encoding, different. If 512 and 512 is the matrix, the phase encoding steps will be that much. And then this is the K space filling. K space filling means frequency domain data, your time domain signal converted into frequency domain signal, and this K space filling will be done. And how the image looks, K space image looks like this. And then this K space image use Fourier transform to constitutes an MR image. Okay, so this K space image changes into MR image. Who is changing this? This is the image processor, that is called imager. The imager is changing K space into patient image. Okay, from here by LAN cable, this image is going to the host PC. I think this is too much. So we will see in another videos. So hope you understood a bit about MRI, how the signals are getting converted. These are all very big topics to learn. Even I am a student, I am learning MR. So if you liked my effort, please subscribe my channel and share to your friends. In coming future, I will try to read more about other things, and I am planning to take another video, to bring another video on artifacts, and maybe in future about CT and X-ray systems, about scintillator technologies, about II systems, about X-ray systems, flat panel, direct flat panel, indirect flat panel. Lot of things are in my mind. I will come up with another videos in future. Thanks for giving your time and watching my videos. See you in my next video. Thanks a lot.